Nobody knows what gravity is. Not me, not Einstein, not the best physicists working today. We know what it does with extraordinary, almost embarrassing precision. But what it is, at a deep level, what's actually happening when that apple falls, nobody knows. And that should bother you. Because gravity isn't some exotic, distant phenomenon. It's the most constant experience of your entire life. It's been pulling on you every second since you were born. You've never escaped it for a single moment, and we cannot tell you what it fundamentally is. Let me show you how deep this goes. When Isaac Newton published his law of gravitation in 1687, he gave the world something extraordinary. One equation, F equals G times m1 times m2 divided by r squared. And suddenly, you could predict planetary orbits, ocean tides, the path of a cannonball, the motion of distant moons around Jupiter. All of it from one formula. It was the greatest scientific achievement in human history up to that point, maybe the greatest ever, and Newton hated it. Not the equation worked. He hated what it implied, because his formula said that two objects, the Earth and the Moon, separated by nearly 400,000 kilometers of completely empty space, somehow reach across that void and pull on each other. No contact, no medium between them, no rope, no mechanism. He called it action at a distance, and in a private letter he wrote that the idea of one body acting on another through empty space, without anything in between to carry the effect, was so philosophically absurd that no sensible person should believe it. Then he published the equation anyway, because it worked. And he wrote 4 famous Latin words, hypotheses non fingo. I frame no hypotheses, meaning I can give you the rule, I cannot give you the reason. So the man who discovered gravity refused to explain it, and every physicist since has been living with that unfinished business. 228 years later, Einstein tried to finish it. He didn't improve Newton's formula. He threw out the entire concept. Newton said gravity is a force. Einstein said there is no force. Gravity isn't a pull, it's a shape. Here's what he meant. Space and time aren't a blank, flat stage where things happen. They're a fabric, 4-dimensional, flexible, and responsive to mass. When you put a massive object in space, it bends the fabric around it. And when another object moves through that region of bent space, it follows the curve. It doesn't get pulled, it goes straight. But straight through curved geometry looks like a curve to us. What we call falling is actually the most natural, unforced motion possible through distorted space. The analogy everyone uses is a rubber sheet. Put a heavy ball in the middle. It sinks down, creates a curve. Roll a marble nearby, and it spirals inward, following the curve. Not because it's attracted to the heavy ball, because the surface it's rolling on has a shape. And Einstein's version of that, applied to actual space-time, makes predictions that are startlingly different from Newton's. Light bends around massive objects, confirmed by Arthur Eddington during the 1919 solar eclipse, exactly as predicted. Time runs slower near massive objects, confirmed by atomic clocks, by GPS satellites, by every experiment we've run. Gravitational waves, ripples in the fabric of space-time itself, predicted by Einstein in 1916, detected by LIGO exactly 100 years later in 2016. The theory works brilliantly, consistently. Every test we throw at it, it passes. But here's the thing nobody tells you about the rubber sheet analogy. Why does the rubber sheet sag when you put the heavy ball on it? Gravity. The analogy for gravity requires gravity to work. We're explaining gravity using gravity. That's not an explanation, that's a loop. And Einstein's equations have the same problem underneath. They describe with perfect geometry how mass curves space-time and how objects move through that curvature. They don't say what space-time is or why mass should have any effect on it at all. The geometry is real. The mechanism is still missing. We replace Newton's mystery with a more beautiful mystery. Now, everything else we know about physics runs through a framework called quantum mechanics. And in that framework, forces aren't just abstract. They're carried by particles. Electromagnetism is carried by photons. When two electrons repel each other, they're exchanging photons. That's the force. The weak nuclear force, which drives certain types of radioactive decay, is carried by W and Z bosons. The strong force, which holds atomic nuclei together, is carried by gluons. All of these particles have been detected. The theories built around them have been tested to extraordinary precision, sometimes matching experiment to 10 decimal places. Gravity should have a carrier particle too. We invented one. We call it the Graviton, and we have never detected it. Not once. Not even close. Here's why that matters, and why it's more than just a missing piece. Quantum mechanics and general relativity are both correct. Both have been confirmed by experiment repeatedly to extraordinary accuracy, but they're mathematically incompatible. When you try to apply quantum mechanics to gravity, when you try to write down a quantum theory of gravity the same way we did for the other forces, you get infinities. Not large numbers. Infinities. The mathematics collapses into nonsense. Two perfect theories of the same universe, and they contradict each other. This isn't a small gap we expect to close next year. It's a foundational fracture in physics. The two most successful frameworks in the history of science cannot both be completely right, because together they produce results that are physically meaningless. Something deeper is missing, something neither theory contains. The graviton, if it exists, would be the bridge, the quantum carrier of curved space-time. But detecting one would require a particle detector approximately the size of Jupiter. The graviton interacts so weakly with everything that even if they're real, we may never catch one directly. We gave the solution a name. That didn't solve anything. Let me tell you something about gravity that most people never stop to think about. It's embarrassingly weak. I mean that precisely. Gravity is, by an almost incomprehensible margin, the weakest of the four fundamental forces. The electromagnetic force is roughly 10 to the power of 36 times stronger. That's a 1 followed by 36 zeros. Here's what that feels like. Take a small fridge magnet. Hold it near a paperclip on a table. The magnet wins. It pulls the paperclip up. What is the magnet beating? The gravitational pull of the entire Earth. Every atom in this planet, 6 trillion kilograms of mass, all pulling down on that paperclip. One cheap magnet against the entire Earth, and the magnet wins easily every time. So why does gravity feel significant at all? Because it adds up and never cancels. Every atom in the Earth pulls on you in the same direction. Mass only attracts, never repels. And gravity has infinite range. It never fully turns off, no matter how far apart two objects are. Add enough mass, and the weakness accumulates into something you can't ignore. But the weakness itself is a profound puzzle. Why is gravity so incredibly feeble compared to everything else? This is called the hierarchy problem, and it has no agreed solution. It's not like we have a satisfying answer that we're still testing. We genuinely don't know why gravity sits so far below the other forces. One live theoretical proposal, taken seriously by serious physicists, is that gravity is weak because it's leaking, not into this universe, but out of it. Some theories involving extra dimensions suggest that gravity propagates through more dimensions of space than the other forces do. The other forces are confined to our 3 dimensions. Gravity spreads into additional dimensions we can't access, so we only experience a tiny fraction of it. Most of gravity is somewhere else, somewhere we can't see or measure. That sounds like science fiction. It's not. It's an active area of theoretical physics. We don't know if it's right. But the fact that physicists are seriously asking whether gravity leaks into hidden dimensions tells you everything about how unsettled this question actually is. I want to tell you something strange, not theoretical strange, practically, measurably, use it every day strange. Gravity slows down time, not as a metaphor, not as a thought experiment. Literally, physically, your clock runs slower when you're closer to a massive object. Einstein predicted this. It falls directly out of general relativity. The stronger the gravitational field, the more space-time curves, and one consequence of that curvature is that time itself runs at a different rate. High up in weaker gravity, time moves slightly faster. Down near a massive object, time moves slightly slower. The GPS satellites orbiting Earth are sitting in weaker gravity than we are on the ground. Their clocks run about 38 microseconds per day faster than clocks on the surface. That sounds trivial, but GPS works by measuring the precise timing of signals from multiple satellites. If you let that 38 microsecond drift accumulate without correcting it, your position estimate drifts by about 11 kilometers per day. Your phone would tell you you're in the wrong city. Every GPS satellite carries onboard software that corrects for Einstein's time dilation. Every time you navigate somewhere, to a restaurant, to a hospital, to an airport, the software in your phone's location system is applying a correction derived from general relativity. You're using Einstein's curved spacetime to find the nearest coffee shop. Black holes take this to its logical conclusion. At the event horizon, the boundary beyond which nothing escapes, time dilation becomes extreme. If you watch someone fall into a black hole from a safe distance, you would never see them cross the horizon. You'd see them slow down, their light stretching to longer and longer wavelengths, dimming, redshifting, appearing to freeze at the edge of the horizon. They'd seem to hang there forever, growing fainter, never quite arriving. Meanwhile, from their perspective, they cross the horizon in a finite time. Time isn't running the same for both of you. This is real. This is confirmed. This is happening. And I still cannot tell you what time is. I can't tell you why mass has the power to stretch it. We can describe the geometry. The geometry is extraordinary. But what time actually is, at a deep level, and why space-time responds to mass the way it does, those questions are open. Now I want to zoom out. All the way out. Because when you look at gravity on the scale of the entire universe, something has gone very wrong. In 1998, astronomers were studying distant supernovae, exploded stars, to measure how fast the universe was expanding. They expected to find the expansion slowing down. Gravity should be pulling everything back together. The further back in time you look, the faster everything should have been moving, and it should be decelerating now. They found the opposite. The universe isn't slowing down, it's speeding up. Galaxies are flying apart faster than they were before. The expansion is accelerating. Something is pushing the universe apart, overcoming gravity on the largest possible scales. We have no idea what it is. We named it dark energy. It makes up approximately 68% of the total energy content of the universe. 68%. The dominant component of everything, and we have no physical explanation for it. We have a number that fits the observations. We don't have a mechanism. And then there's dark matter. Galaxies rotate in a way that doesn't match the gravity of their visible stars and gas. Stars at the outer edges of galaxies move too fast. By the laws of gravity, they should have flown off long ago. They haven't. Something invisible is providing extra gravitational mass to hold them in. We call it dark matter. It makes up about 27% of the universe. Do the arithmetic. Dark energy, 68%. Dark matter, 27%. Ordinary matter, stars, planets, gas, dust, everything we've ever seen or touched or detected with any instrument, about 5%. We understand 5% of the universe. The other 95% is a label on a mystery. And the mystery is directly tied to gravity, because it's gravity that doesn't add up at these scales. The force we thought we understood best breaks down completely when you look at the whole picture. Unless you invoke two invisible, undetected, unexplained substances that together make up almost everything. So let's come back. Back to Earth. Back to the apple. What do we actually have? We have Newton's formula. Perfect for engineering, perfect for space missions. Accurate enough to land a probe on a comet moving at 135,000 kilometers per hour. We have Einstein's geometry. Beautiful. Confirmed, running in your pocket every time you check your location. And we have quantum mechanics, precise beyond any other theory in science. And we cannot connect them. The quantum theory of gravity doesn't exist. Every attempt to write one produces infinities. The mathematics says something is fundamentally missing from our picture. We have a carrier particle, the graviton, that we've never detected and may never be able to detect. We have a force that is inexplicably, absurdly weaker than every other force, with no accepted explanation for why. We have time itself bending near massive objects without any deep understanding of what time is or why mass should affect it. And we have a universe where gravity, extrapolated to the largest scales, fails to match what we see unless we fill the gap with invisible, undetectable stuff that comprises most of everything. This is the honest picture. And here's what I want you to understand, what I think is absolutely crucial. The word gravity sounds like an answer. You ask why the apple falls, and someone says gravity, and you nod, and the conversation stops. But gravity is not an answer. It's a name for a question. It's pointing at something real, something that is definitely happening, and saying, this thing, right here, we're still figuring out. That's what naming something does. It gives us a handle on it. It lets us talk about it, calculate with it, use it in equations. But the name is not the understanding. This is the mistake, the one Feynman spent his whole career fighting against. We confuse the map for the territory. We confuse the label for the thing. We know the rules of gravity with breathtaking precision. We don't know what gravity actually is. Here's what I find beautiful about that. We are creatures who evolved on a savanna. Our brains were built by evolution to track moving things, to recognize faces, to navigate short distances, to avoid predators. We were not built to understand 11-dimensional spacetime or quantum field theory. We were built to survive, to eat, to reproduce. And yet, somehow, with these same cobbled-together brains, these organs that are really just very sophisticated survival machines, we figured out that the universe is 13.8 billion years old. We figured out that space bends. We figured out that time slows near mass and proved it with clocks. We detected a ripple in space-time from two black holes colliding 1 billion light-years away, a ripple that moved the LIGO detector by less than 1,000th the diameter of a proton. We did that, with brains that were originally built for something entirely different. That's extraordinary. It's almost unreasonable that we've gotten this far. But we hit walls, real ones, and the wall we hit with gravity is the biggest one in physics right now. The place where our two best theories collapse into each other and produce nonsense. The place where the universe is telling us clearly, mathematically, unmistakably, that something is missing from our picture of reality. Something we haven't thought of yet. And here's the thing about walls like this. Every single one of them in the history of science has eventually become a doorway. Not always in the way people expected, not always quickly, but the walls are where the real discoveries are waiting. Newton's wall, action at a distance, became the doorway to general relativity. The incompatibility of classical mechanics with electromagnetism became the doorway to special relativity and quantum mechanics. Every time physics got stuck, something new was on the other side of the sticking point. Something that changed how we understood everything. The war we're at with gravity, the quantum gravity problem, the hierarchy problem, dark energy, dark matter. These aren't signs that physics is broken. They're signs that something genuinely new is waiting to be found. Some concept we don't have yet. Some way of thinking about space, time, and mass that nobody has worked out. And whoever works it out, whenever that happens, will have changed our picture of reality more fundamentally than Newton did, possibly more than Einstein did. Gravity has been pulling on you every second of your life. It's shaped every structure in the universe, every star, every galaxy, every planet, every atom in your body got here because gravity pulled gas clouds together until nuclear fusion ignited. It has never let you go, not for a microsecond. And we still don't know what it is. I think that's wonderful. I genuinely do. Not knowing isn't the embarrassing part. Not knowing is the interesting part. The questions we can't answer yet are the most valuable things we have, because they're pointing directly at the places where our understanding of reality is incomplete. Every mystery we've ever solved started exactly here, as something familiar that nobody could explain, as something that everyone experienced and nobody understood, as something that sat there in plain sight, pulling on everything, waiting for someone to refuse to stop thinking about it. The apple fell for billions of years before Newton watched it fall. It'll keep falling long after all of this is figured out. The question isn't going anywhere. Neither are we.